Hello there. For our last lesson in gases, we're going to combine what we've learned with the principles of stoichiometry. And so lots of reactions, of course, happen in the gaseous state. Here's a classic one from my kitchen, which is methane, part of natural gas, reacting with oxygen, producing carbon dioxide and water. Combustion, as you know. So let's have a look at how some of these things can be simplified, or some of the details you'll have to keep an eye out for when you're dealing with gases in a chemical reaction. The first thing to remember is that the proportion of gaseous volumes is going to follow the balanced equation. So if you balance an equation with water, making oxygen and hydrogen gas, and to balance that you need 2 and 2, that means that the volumes that will be required will follow that same ratio. You'll get 2 parts hydrogen for every 1 part oxygen, as you can see from this Hoffman apparatus, as we mentioned earlier, right? That has to be the hydrogen, and this guy here has to be the oxygen. So that means you can use the coefficients from a balanced equation, the 3 and the 1 and the 2 here, as a ratio of volumes as well as a ratio of moles. So sometimes you can get away with not having to convert it into moles if you have volumes and if the conditions aren't changing, right? So it says, what volume of hydrogen would you need to react with 10 liters of nitrogen in the following reaction? So hydrogen to nitrogen. So if I want to know the volume of hydrogen, and I know I have 10.0 liters of nitrogen that's reacting, well, I can just use the ratio from the balanced equation, because it's not just a mole ratio, it's a volume ratio as well. So it's 1 mole of nitrogen to 3 moles of hydrogen, and so 3 times 10 is 30 liters of hydrogen would be needed. If there's gases involved in your stoichiometry, but it's with other states like liquids, then you're going to have to use your ideal gas law if the conditions are not standard. So if you can't use your 22.4 liters per mole or 24.8 for the ambient standard temperature and pressure, then you're going to have to use ideal gas law. So let's do this example here. First of all, we'll find the moles of oxygen that is needed, and then we're going to use ideal gas law to get the volume. So we'll start with moles. We have 10 grams of the octane, which is this guy, and so C8H18, and I've just worked it out. It's 114 grams per mole of C8H18, and the ratio is 2 moles of C8H18 to 25 moles of oxygen. So let's work that out. So 10 divided by the 114 times 25 divided by 2. And so I would get pretty close to 1. 1 point, how many sig figs I got here? 1.096 moles of oxygen. So then if we want to know the volume, we know that PV equals nRT. So volume equals nRT divided by P. So the moles is 1.096 moles of oxygen. R is 8.314 kilopascal liters per mole Kelvin. The temperature is 10 Celsius, so that's 283 Kelvin. And the pressure is 90 kilopascals. So let's see what that comes out to. 1.096 times 8.314 times 283 divided by 90 equals 28.7. 28.7 liters. There you go. Alrighty, now if you have a reaction where both of the reactants are gases, then you can use that as a shortcut for finding limiting reagent. You don't have to convert to moles first. You could just use the mole ratio from the equation, right? So for C8H18, it's 5 liters of vaporized octane, and we've got 50 liters of the oxygen gas. And so if we divide this by 2 and divide this by 25, 5 divided by 2 is 2.5, 50 divided by 25 equals 2.0, and that means that the limiting reagent here is the oxygen. So that one is your limiting reagent. And then it says what volume of water will form if these conditions do not change. Well, this is water is a gas as well, so you can just use the same ratio. We're going to start with our limiting reagent, which is the oxygen. So we want volume of water as a gas, and we're going to take the 50 liters of oxygen, and we just use the ratio. You're going to get 18 liters of water for every 25 liters of oxygen. And so that ratio will work out to 50 times 18 divided by 25 equals 36 liters of water vapor will be formed. There you go. Alrighty, so looking at this reaction, we've got the octane back as a liquid here, and we're asked for the volume of a gas, and we have the volume of the octane as a liquid. So we need the density in order to get to mass, and then we can use our ideal gas law at the other end to work out the carbon dioxide that was produced. So we'll start by looking for moles of CO2 and use the 50 milliliters of octane, H18. And then we're going to use the density to go from milliliters to grams. We got 0.85 grams for every 1 milliliter. And then octane was 114 grams for every mole. And then the ratio was 16 moles of CO2 for every 2 moles of C8H18. Okay, so let's see what that comes out to. We got 50 times 0.85 divided by 114 times 16 divided by 2 equals. So I get 2.98 moles of CO2. Then if you want the volume, so V equals nRT divided by P. We've got the moles there, 2.98 moles of carbon dioxide. R is 8.314 kilopascal liters per mole Kelvin. And the temperature is 34 Celsius, so that's 307 Kelvin. And then we're going to divide by the pressure, which is 95 kilopascals. So you can see everything cancels out there. Moles cancels out with moles, kilopascals cancels out, Kelvin cancels out, and we should end up with liters. So let's see what that comes out to. 2.98 times 8.314 times 307 divided by 95 equals, wow, quite the volume, 80 point, how many digits we got here? Most of these are 2, so just 80 liters. There you go. Alrighty, so the last problem we're going to look at here is when a gas is being collected over water. And whenever that happens, you should keep in mind that there's going to be some water vapor in with that gas. So you're going to have to subtract that first before you're going to do the rest of your problem solving, stoichiometry, ideal gas, whatever it may be. So, so the total pressure is going to be equal to the pressure of the hydrogen plus the pressure of the water vapor that's in there. So if you want just the pressure of the hydrogen, we're going to have to take the 95 kilopascals, that's the total pressure, and subtract the 2.3 kilopascals, which is just the water vapor. And so that gives us 92.7 kilopascals of hydrogen pressure. The next step here is to figure out how many moles that is. So you're going to use the good old ideal gas equation, PV equals nRT. So N equals PV divided by RT. The pressure is the 92.7 kilopascals. The volume is 0.020 liters. The R is the constant, 8.314 kilopascal liters per mole Kelvin. And the temperature is 20 Celsius, which is 293 Kelvin. So just check, make sure everything cancels here. We got kilopascals canceling, liters canceling, Kelvin canceling, which means we're going to leave us with moles. And we'll put the answer over here just for space. So 92.7 times 0.02 divided by 8.314 divided by 293 equals. And I've got a very tiny number here, 0.000763 moles. Great. So now we can finish this off. It says what mass of magnesium would have to react with HCl? Oh, I didn't give you an equation. All right, let's write it down right now. So magnesium plus HCl is going to react to give us the hydrogen gas plus some magnesium chloride. And so it means we're going to need 2 of these. I think everything else balances out. So our ratio is going to be, oh, that's nice and easy. It's just 1 to 1. So this is moles of hydrogen that we're going to end up with. And so if we want to know the mass of the magnesium, then we're going to take that tiny amount of hydrogen, and we'll use the mole ratio. We're going to get 1 magnesium reacting for every 1 hydrogen, so that gives us moles of magnesium. And then to get the mass, it's 24 grams for every mole of magnesium. Okay, moles of hydrogen cancel out, moles of magnesium cancel out, end up with the mass. Looks good, let's work it out. So times 24 equals a very tiny mass of magnesium. So 0.0183 grams. There we go. All right, that's about as tricky as it gets. We'll talk to you soon.